velocity of the object. So the kinetic energy is a scalar quantity, right? So it's scalar, it's not a vector. And this quantity has a magnitude which is half times the mass, the magnitude of velocity. The magnitude of velocity squared, which is the dot product of the velocity vector. So as in a scalar representation, it is half times the mass times the magnitude of the velocity squared. And this gives me the total kinetic energy in an object. So the difference in the kinetic energy of an object, which is delta T, relates to another scalar, which is called the work. So to move an object from one point to another point, work will have to be done by an applied force on the object. So as work is done on an object, the velocity of the object change. Maybe in position 1, the velocity of the object is v1, and as work is done on the object by the force, the velocity becomes v2 in position 2. So the difference in kinetic energy is the kinetic energy in position 2 minus the kinetic energy in position 1. And this difference or increase of energy in kinetic energy is equal to the work done. So this kinetic energy, this difference in kinetic energy, is actually supplied by the force which acts on the object. So there is a relationship between the kinetic energy, and it's indeed a very important relationship between the kinetic energy and the work done by the force. So literally, the difference between the kinetic energy, or the increase or decrease in the kinetic energy, is equal to the force, to the work done by the force, or the work done against the force by the object. So the work can be positive, that is, if the velocity in position 2 is higher than the velocity in position 1, meaning that work is done by the force to increase the kinetic energy. Work can be negative if the velocity in position 2 is less than the velocity in position 1. Then that means you have negative work. That means that work is done by the object against the applied force as it moves from position 1 to position 2. In terms of the force, we know, again, this is a review, as I said, an overview. We know that the work done can be related to the force that is acting and related to the two positions. This is position 1, which is position R1, and this is position 2, which is position R2. So the work done is actually equal to the integral of the force, which is a vector, in a dot product with dr, which is the differential of the position, and this integral evaluated between R1 and R2, which are the two positions, position 1 and position 2. So literally what we have here, we have an object has a velocity v1 at the position vector r1, right? And has a velocity v2 in a position r2. And this change in velocity and in position is produced by a force F. So the change in kinetic energy of the object as it goes from position 1 to position 2 is equal to the work done by the force. Okay? So this is a very important relationship. And quantum mechanics is all about energy. So we have to remember these definitions of energy in classical mechanics, and later on we will see how we discuss energy when we talk about quantum mechanics. So, for a special class of forces, and luckily this special class of forces almost cover all forces in physics. This special class of forces are called conservative forces. And for these conservative forces, it is possible to find a scalar function, u of r. So you have a force, and then you have a scalar function, u of r, such that this integrand here, which we use to find the work, F dot dr, can be written as a complete differential. Remember, F dot dr is a dot product, so it gives you a scalar. Now, if you can get a function u of r, which is a scalar function, and the differential of this scalar function exactly matches F dot dr, or in other words, if you can write the vector F, which is the force, as the grad of this function, okay, minus nabla u of r. So these two relations are exactly the same. Remember, this nabla, if you remember your vector analysis or vector algebra, this nabla is an operator, and its derivative with respect to space along the three mutually perpendicular directions. So, force can be extracted from this scalar function. Now, this scalar function is therefore very important, which is tied up with conservative forces. This scalar function u is referred to as the potential. So every conservative force has a potential. And you can always get the force from this potential by applying the grad operator. Or you can obtain the scalar potential from the force by solving this equation. Now, let me give you an example of a force and a scalar potential. And this is a very important force, which is an electrical force, Coulombic force. What is the Coulombic force? F. And for a Coulombic force between charge, it is 1 over k, where k is a constant depending on the surroundings. But then you have q1, maybe q2, where these are two charged, over r squared. This is the Coulombic force between a charge q1 and another charge q2, separated by a distance r. Okay, 1 over k, or k is 4 pi epsilon naught. Now, with this Coulombic force, there is a potential at any point, and the potential is proportional to 1 over k and 1 over r. So you see that there is a scalar potential, V. This V is what we mean by U of R. So this force, which is a Coulombic force, has a Coulombic potential, or a scalar potential function, U of R. And you can immediately see that you can get this F by differentiating. You see, if you're talking about one direction, nabla becomes just a derivative with respect to r. And if you differentiate with respect to r, 1 over r, you get the r squared. Okay? So actually, this force, Coulombic force, relates to this potential. And also, there are all other types of forces like gravitational force, the force of attraction due to gravity, and there is a potential, scalar potential associated with that force. Okay? So, now, if this is the case, and if this integral becomes very simple. This integral simply becomes 2 at R2, because this is a complete differential. Look, this is this. So if you put minus dur here and integrate, you get ur2 minus ur1 for that integral. So that integral becomes very easy in terms of the scalar potential. So what happened in this case, W, which is the work done here, becomes the difference in the scalar potential at position 1 and position 2. So we can put this relation here instead of W, right? And then we can rearrange the equation and say the kinetic energy in position 1 plus the value of the scalar potential in position 1 is equal to the kinetic energy in position 2 plus the value of the scalar potential in position 2. Now, this scalar potential is normally referred to as the potential energy. So, the potential energy is the value of this scalar potential in position 1. And the potential energy here is the value of this scalar potential in position 2. So what do we have here? This is our kinetic energy. This is our potential energy. So kinetic energy plus potential energy equals total energy. So what we have on this side here is total mechanical energy at position 1, which is this one here, right? And what do we have here? Total kinetic energy in position 2 plus potential energy in position 2. So what we have here is total energy, or total mechanical energy at position 2. So what we have here is that the total mechanical energy at position 1 is equal to the total mechanical energy in position 2 is equal to the total mechanical energy at position 3, position 4, etc. So what we really have here is conservation of energy. And that is true for conservative. So conservation of energy is true for conservative forces. So conservative forces comes from conservation of energy, for which energy is conserved. So this is very important consideration. Now, one last point that I'd like to review, one last parameter, is the impulse, L, which is a vector. And this is a vector that relates the difference in the momentum of an object. So if the object has a velocities v1 and v2 at times t1 and t2, remember here we're talking at velocities v1 and v2 at positions r1 and 2. Now here, observe that we're talking at an object which has velocities v1 and v2, but at times t1 and t2. Then the difference in the momentum, which is a vector, momentum is a vector, so the difference in two vectors is a vector too. So this is the momentum at time t2. This is the momentum at time t1. The difference in the two momenta is equal to a vector L, which is actually the impulse. And how do we define the impulse? The impulse is the integral of the force vector over the time interval t1 to t2. So what we have here is the linear momentum, linear impulse principle, which simply says the difference in the linear momentum of an object between times t1 and t2 is equal to the linear impulse L. So this Newtonian description of mechanics works very well, okay, in the classical scheme. What do we mean by the classical realm or scheme? What we mean is that the sizes of the objects under consideration and their speeds are in the range that can be perceived by our ordinary senses. What do we mean by that? We mean that we're talking about objects that are commonplace, objects that we see with our senses, with our eyes, okay? Objects that are big, objects that are sizable, bodies, humans, trains, cars, aeroplanes. All these types of objects are objects that we can see and we can perceive, and these are large objects. These objects moving at the speeds that are, again, easily measured and perceived. The type of speeds that we walk with, the type of speeds that the cars move with, even the kind of speeds that an aeroplane or even a rocket moves with. These speeds are small, and the objects are large, and quantum and classical mechanics works very, very well. It works very well in these cases. And in fact, most of engineering is very, very satisfied with applying, most engineering disciplines are very satisfied with applying classical mechanics. Look at all, different fields of mechanical engineering, different fields of civil engineering, etc., use classical mechanics, and classical mechanics works very well for all these kind of systems, in these types of engineering. However, in electrical engineering, things are somewhat slightly different, and particularly when we talk about nanoelectronics or nanotechnology or objects of very small that we cannot see with our senses, with our eyes, like electrons, for instance, classical mechanics becomes a little bit of a disadvantage. So we have to come up with a new brand of mechanics that takes care of such small particles. Same time, these small particles, like electrons, for instance, move with very high speeds, very high velocities. So much, much higher than velocities of rockets or airplanes, etc. So again, classical mechanics will not serve us well if we try to use it for these kind of objects. So in dealing with objects that are of atomic sizes or smaller, such as electrons, we need to use quantum mechanics to describe their motion. So the reason that we revised classical mechanics, first of all, because we would probably use some of it later on, but also we wanted to contrast it with what's coming. And what's coming is quantum mechanics. But then before we go into quantum mechanics and talk about quantum mechanics, let us do a few things. Let's talk about a few things that would prepare us to understand quantum mechanics. And the first thing that I'd like to talk about is electromagnetic radiation. And electromagnetic radiation is a very important area in all kinds of applications. It's a very important area in science, particularly in physics, but it also has a lot of applications in engineering. And electromagnetic radiations are very important, and so let's see what we're trying to do here in terms of electromagnetic radiation. We know that electromagnetic radiations are waves. So, literally speaking, they are waves propagating like this, just like what we see in waves, you know, if we're standing in the shore near an ocean, for instance. So waves propagate, and they have very, very clear properties that we study in optics. We probably did it in our early physics classes. They diffract. So one property of waves is that you get diffraction. You also get interference. These are very important characteristics. What do we mean by that? If we have a wave going like this one, right? And if we have another wave going like this one, okay? So you can clearly see that the bottom of this wave coincides with the top of this wave. The top of this wave, the bottom of this wave, and so on. So this is a wave going this way maybe, and this is a wave coming this way. If you add these waves, then they cancel one another, and then you just get no wave, or a zero wave. This is called interference, destructive interference. Okay, so waves interfere, and in this case, interference. Okay, so in this case, they interfere destructively. If the top and the top meet, right, then what will happen is they will interfere constructively. If they happen to be in phase like this one, then when you add them up, you get a very large wave. So in this case, they interfere constructively. So waves here interfere constructively. So constructive interference. Okay, diffraction. Now, if you have an opening, okay, so let me clear out this. Clear out this region here. Okay. So if we have again an opening here, and if we have a wave coming through this opening, and if we have a screen, say this wave is light, so you expect this wave to go through and hits here. But that does, what it happens is it will hit at a wider range. Okay, so the image that you see is wider than the opening, okay, through which the wave propagates. So this is called diffraction. Okay, so waves diffract, right? But contrast it with if you have an object. If you just have a small ball here and you have a screen here and the ball goes through here, then it will hit the screen here. So there is no diffraction. It will never hit anywhere up here or down here. So diffraction meaning that the image of an incoming wave through an opening would be in a larger area in the screen. So waves, we know them and we know their properties, diffraction and interference. Electromagnetic radiation is made up of oscillating electric and magnetic fields. So you have an electric field, E, vector, and a magnetic field, B. And they oscillate, they wave. And most important group of electromagnetic radiation is visible light. Light is an electromagnetic radiation. So what happens in an electromagnetic radiation? Electromagnetic radiation is a wave, right, of electric field along the x direction maybe, and a magnetic field in the b direction, and both waves propagates in the z direction. So maybe this is electric field, this is magnetic field, and the direction of motion is in this direction. So it's two oscillating electric and magnetic fields, they form the electromagnetic radiation. Light, visible light, is an important component of electromagnetic radiation. So we know very well light is a wave, okay? And it's an electromagnetic radiation, okay? But that was the case until 1900. There was this very important experiment in physics that threw doubts on all laws of physics because people observed it but they couldn't understand it until a German scientist called Planck, Max Planck, came up with a very pioneering theoretical work. And actually the experiment, the physics experiment that people could not explain at that time in the 1900s, it's the radiation, the electromagnetic radiation that comes out of a body, which they call black body. If they heat it, if they increase the temperature of the black body or this body, electromagnetic radiations come out of this body. So they tried to look at the intensity of this electromagnetic radiation as a function of the frequencies, because we know that waves and oscillating waves have frequencies. So they wanted to measure that, and indeed they measured that, and then they tried to explain it theoretically with the laws of physics that were existent prior to 1900. And they couldn't do that with the wave properties of radiation, of electromagnetic radiation. So, with electromagnetic radiation, we cannot explain this black body. Okay? So, in that case, Planck in 1901 came up with a very interesting proposition. What he said is the following. He said, let us think of this electromagnetic radiation as particles. Particles meaning bodies, not just radiation. Okay? You can think of electromagnetic radiation as waves. Okay? Going in this direction. Okay? So they could be waves, right? Or you can equally and rightly so think of electromagnetic radiations as particles, very small particles, okay, all in lump sum, okay, going in this direction. So many particles, millions, trillions, zillions of these particles moving in this direction. Okay? So you can think of them as particles. Now, how can we think of them as waves and at the same time think of them as particles? It's very difficult to conceive, but this is now commonplace thinking. Okay? Particle nature. That's why we have here particle nature of electromagnetic radiation. So we're going to think of electromagnetic radiation as waves, if we like, or as particles. Either way of thinking at electromagnetic radiation is right. Okay, these particles, what are they? These particles are some discrete bundles of energy. These particles are all energy, and they're called photons. So each one of these particles is called photons, or a photon. Now, each photon has an energy E, because electromagnetic radiation has energy. So this energy is carried by these particles, the photons. Each photon has an energy E. And this energy E depends on the frequency. So you see, frequency is the property of waves. So we are not abandoning the idea of electromagnetic radiations being waves. They are waves. But I can also think of electromagnetic radiation as particles. And the energy of each particle, which we call the photon, depends on the frequency, nu, of the radiation or of the electromagnetic wave. The energy of each particle or photon is h, a constant h, times the frequency, nu. This constant h is a very important constant. This constant h is 6.626 times 10 to minus 34. Very, very small indeed. Joule second. So h is a constant, which is energy times time, but it's a very, very small constant, 10 to minus 34 joules second. So when we multiply this constant h by the frequency, we get the energy of the photon, each single photon of electromagnetic radiation. So this energy of the photon is very, very, very small when we think about it in terms of joules.